Hello guys, welcome to your channel Himanshi. In this video lecture, we'll cover common ion effect, solubility product, salt hydrolysis, purpose solutions in detail. And I bet after this video lecture, most of your doubts regarding the ionic equilibrium portion would be covered, would be solved. So without further ado, let's begin. So the first topic is common ion effect. Now what is common ion effect? As the name suggests, there will be a common ion. So you know that when we say there is something common, for having something common there must be at least two individuals. That's why we can compare and say that so this is the common or the similarity between these two. So therefore, for common ion effect to be there, there have to be two electrolytes. So if we consider the two electrolytes as ammonium chloride and ammonium hydroxide, these are called electrolytes because in ionic solution they will ionize to give us the ions. That's why we call them as electrolytes. So now tell me, what is the similarity between these two? The similarity or the common thing between these two is the first ion. Ammonium ion is the common ion between these two electrolytes. Out of the two electrolytes, ammonium chloride and ammonium hydroxide, the one which is a stronger electrolyte is ammonium chloride. Ammonium chloride is a stronger electrolyte. It will ionize more than ammonium hydroxide ionization. So what happens is, whenever there is a competition between two individuals which are in the same field, the one which is stronger will compete over the other and it will be on top. So that same concept applies in chemistry as well. Ammonium chloride is a stronger electrolyte and ammonium hydroxide is a weaker electrolyte. So ammonium chloride will take over the ionization of ammonium hydroxide. It will decrease the ionization of ammonium hydroxide. This is what is common ion effect is all about. So let's look at the definition. When the two electrolytes having common ion are taken in the same solvent, only in the solvent the electrolytes are gonna be ionizing, then the degree of the ionization of the weaker electrolyte decreases. So I've told you how it works. The example which I told you is ammonium chloride and ammonium hydroxide. It dissociates to give us the ammonium ion and hydroxide ion, and ammonium chloride dissociates to give us ammonium and chloride ion. This ammonium ion is the common. It's the common ion. Out of these two, ammonium chloride is a stronger electrolyte. So what happens is, ammonium chloride is a stronger electrolyte. It will ionize more compared to ionization of ammonium hydroxide. So since it will be ionizing more, the concentration of the ions, ammonium ion generated from ammonium chloride and chloride ion, will be more compared to this. Another example of common ion effect is H2S, hydrogen sulfide, and HCl. There is one important question which also comes from this topic. If you have done salt analysis, in the cation analysis, in the analysis of second group elements, we always add HCl first and then we pass the H2S gas for the precipitation of second group elements. Why is this so? Why do we need to add HCl first and only then we proceed for passing the H2S gas? So this is so because since HCl, hydrochloric acid, it is a stronger electrolyte compared to H2S, it will ionize more into H plus ions and chloride ions, and it will decrease the ionization of H2S into H plus ions and sulfide ions. So here look at this, the common ion is H plus. Due to this common ion effect, since H2S will be dissociating or ionizing less, therefore the concentration of the sulfide ions that we get in the reaction mixture will be less. So if we get the lesser concentration of sulfide ions, there is a concept of precipitation using solubility product and ionic product, which I'll be telling you later in this video lecture only. So for this portion, just understand that in order to get lesser concentration of sulfide ions, we add HCl first. The concentration of sulfide ions generated is just enough for the precipitation of only group 2 elements and not for the precipitation of group 4 elements. You must be doing salt analysis in class 12th, so I think that it will not be this easy because you are not doing it practically, but you'll understand it. So there's a concept known as solubility product and ionic product, which is applicable here. So what happens is, whenever the solubility product, which we denoted by KSP, is greater than the ionic product, let's say we denote it by Q, when the solubility product is greater than ionic product, then there will be no precipitation. Why there will be no precipitation? Because its solubility product is higher. Higher the solubility product means ultimately there will be high solubility. If the solute is highly soluble in the solvent, how it is possible for it to precipitate? Therefore, there will be no precipitation. And if KSP value is lower than the ionic product, by ionic product I mean that the tendency to form ions or to form to ionize. If there are more ions, there will be tendency for them to aggregate together, coagulate, and ultimately deposit at the base of the reaction mixture, of the base of the beaker, which means whenever the ionic product is greater, there will be precipitation. It will occur. So here the sulfide ion concentration generated will be lesser because HCl is a stronger electrolyte. It will hinder the dissociation of H2S, which is a weaker electrolyte. So the concentration generated is just enough to exceed the solubility product of the group 2 cations, to exceed the solubility product for the group 2 cations. So what happens is, for group 2, the ionic product exceeds the solubility product, so there will be precipitation occurring. But the ionic product is less than the solubility product for further group cations. Hence, they will not be precipitated along with group 2 elements. In salt analysis or here cation analysis, we don't want the cations to come at once. We want them to come in a stepwise manner. That's why the common ion effect here is of great importance. Now let's talk about solubility product. Consider an electrolyte barium sulfate, BaSO4. It will ionize to give us the barium ions, Ba2 plus, and sulfate ions. So similar to equilibrium constant calculations, we can write the KSP or the solubility product. It's same like writing the equilibrium product, equilibrium constant. We write KSP as barium ions into sulfate ions. We don't write barium sulfate because it's the pure form. So this is the solubility product. If the solubility of barium ions and sulfate ions is S, what is solubility? Solubility is same as the concentration value. If I'm saying solubility or concentration, it means the same thing only. So if the solubility of or the concentration is S, both will be S because these are equimolar. We substitute concentration values by writing S, which is the solubility. KSP therefore becomes product of S into S, which is equivalent to S square. So in many competitive exams also, they will be asking you the KSP value calculations. You just need to get the answer in the form of S square. So that's why it's a very, very important thing to know. Another example is the ionization of calcium chloride. It will ionize to give us the chloride ions as well as calcium ions. We write KSP as product of concentration of calcium ions into concentration of chloride ions, since there was 2. So while writing equilibrium constant also, the stoichiometric constant goes on top of the concentration of that ion. So that's why we are writing KSP as calcium ion concentration into chloride ion concentration to the power of 2. These are not equimolar now. The ions formed are not equimolar. If suppose the solubility of calcium ion is S and the solubility of chloride ions is 2S, because the ions formed are twice the number of the ions which are formed of calcium. That's why we write 2S here. We can write the KSP as KSP value as S into 2S whole square. Now always remember what is the difference between writing equilibrium constant and solubility product is that we substitute equilibrium stoichiometric coefficient here, as well as we write it here also. So this is one important thing which and most of the children get confused while writing solubility product. So 2s whole square, it becomes 4s square into s. KSP becomes 4s cube. Another important example is aluminium chloride ionization. Will ionize to give us aluminium ion as well as chloride ions. If the solubility of aluminium ion is S, then solubility or the concentration of chloride ions will be thrice the solubility of aluminium ions, because they are generated thrice times of aluminium ions. So we write it as 3s. So we write KSP as concentration of aluminium into chloride ion whole cubed. We write aluminium ion concentration as S and chloride ion concentration as 3s whole cubed. 3 cube is 27. So in total it becomes 27s4. I hope the concept of solubility product is quite clear now. Another example is, if suppose this is general formula of any electrolyte, we write it as A2X3. How you will show the ionization? What we do is, whatever which is given in subscript, we write in front of that element. So it will become 2A, and the subscript of another element goes in the power, so it becomes 2A 3 plus. And always remember, whenever an electrolyte is given, the first element will be is always gonna be cation. If this is an electrolyte AX, first element will be cation and the second one will be anion. Together they will form give a neutral electrolyte AX. So first one is the cation 2A 3 plus, and the second is 3x 2 minus. Now how to know whether you have written this correctly? Now note that the value of cation and anion is always equal. 2 into 3 6, and 3 into 2 minus 6. So plus 6 minus 6. Only then, whenever this value number is equal, then they will combine together to give us the neutral salt or the electrolyte. So this is an important trick to know whether you have written the ionization correctly or not. We can write the KSP value now. If the solubility is 2s, here the solubility will gonna be 3s. We write aluminium 3 plus twice into x2 minus whole cubed. Substitute the solubility values here. What we get is 4s square into 27s cube. We get 108s to the power of 5. So it's very easy to calculate KSP. You just need to know how to write the KSP solubility product. So this is another numerical from your in-text examples only. The question says the values of solubility product of two sparingly soluble salts, which is nickel hydroxide and silver cyanide, are this and this respectively. So tell me which salt will be more soluble. Now remember that solubility product is directly proportional to solubility. Higher the solubility value, higher will be the solubility product as well. So the solubility product is higher for which is the higher one? For nickel hydroxide, solubility product is 2 into 10 raised to the power minus 15, and for silver cyanide it is 6 into 10 raised to the power minus 17. Which is higher number? So this is a higher number, because now here don't look at this 17, it is in negative value. This is higher. Solubility product of nickel hydroxide is higher, so it will be more soluble. In NCERT it is as they have solved it like this. If we write the so both methods are correct, it's just the shortcut way that I've taught you. Sorry. If we write the solubility of nickel hydroxide ions as S1, so we'll get the solubility product as this, and there they have substituted this value, 2 to 10 raised to the power minus 15 is equals to 4s1 cubed. we can easily solve to find out the solubility value. But you can easily know that I've told you that solubility product is directly proportional to solubility only. And for silver cyanide, they have shown it like dissociation into silver ions and cyanide ions. If the solubility is S, we write the Ksp as S. If we write it as S2, we can calculate the solubility for the dissociation of silver cyanide as well. From either of these methods, we get the same answer only. So it's up to you. If it's a numerical question, then I think you have to solve it only. Let's look at another topic. Buffer solutions. What are buffer solutions? Buffer solutions are those solutions which resist the change in pH upon addition of small amounts of acid or base. It's quite true, if you add a huge quantity of acid or base, pH is going to change. Even buffer solution won't do anything in resisting the pH change. But if you add water, that is on dilution or addition of small amounts of acid or base, this buffer solution will be resisting a change in pH. There are two types of buffer solution, namely acidic buffer and basic buffer. Acidic buffer is composed of a weak acid and a salt of weak acid and strong base. Weak acid, common example is acetic acid, and the salt of weak acid and strong base will become sodium acetate. Sodium ion comes from strong base, which is sodium hydroxide. So whenever and weak acid is acetic acid, so the salt which will be formed from these two will be sodium. We remove water, so the salt which we'll be getting is sodium acetate. A basic buffer is composed of weak base. A weak base will be ammonium hydroxide and salt of a weak base and strong acid. So always remember, whether it's acidic buffer or basic buffer, it will always be composed of, if it's acidic buffer, it will always be composed of weak acid and salt of weak acid plus strong base. Here, the salt of weak base and strong acid will become ammonium chloride. Strong base is HCl and weak base is ammonium hydroxide. Again, just remove water and ultimately we will get the salt, which is ammonium chloride. Just remember the examples. If it comes, then you can easily answer. There is not more in detail from this portion. Now let's come to salt hydrolysis and the pH of their solutions. So when is a salt formed? Salt is always formed from reaction between acid and base, which is also generally called as neutralization reaction. Whenever acids and bases, they combine in definite proportions, followed by their ionization in water, only then salts are formed. So after ionization, then there is an interaction between water and the cations and anions which are formed by ionization. Then this interaction is known as hydrolysis. So salt is formed by reaction between acid and bases in definite proportions. Only when a salt is formed, it will ionize in water, and after ionization it will interact with water molecules. The cation and anion form will interact with water, and this interaction is named as hydrolysis. I hope you understand what is salt hydrolysis. It is composed of two steps. Only after the hydrolysis, the pH of the resulting solution will be affected as a result of hydrolysis. Let me tell you, for example, take the example of sodium hydroxide, which is a base, and HCl. They will form sodium chloride and water. So the salt form will ionize Na plus chloride ions. After the ionization, it will interact with water. So Na plus will react with water to give us NaOH, and NCl minus will interact with water to give us HCl. So it is a neutral solution. We get strong base and strong acid back. So the pH will be 7 or around 7 only. Now let's see the type of salt hydrolysis. If we have a salt made up of weak acid and strong base, what will be the pH of the resulting solution? salt of weak acid, and strong base will be sodium acetate. So after sodium acetate, we have it will ionize to give us acetate ions and sodium ions. Okay, after this ionization, it will react or interact with water molecules to give us the acetic acid and NaOH back. So we are getting a weak acid back and a strong base back. So what will the pH? pH will be of the stronger component. The stronger component is the base. So the pH of this salt hydrolysis is always be going to be greater than 7, since it will be a basic solution. Another example is a salt of strong acid and weak base. The salt is ammonium chloride. The ammonium chloride will ionize to give us ammonium ion and chloride ion. After the ionization into cation and anion, it will interact with water to give us ammonium hydroxide and HCl. Now out of these two components, which is a stronger one? Now HCl is a stronger acid compared to ammonium hydroxide. It is a weaker base, ammonium hydroxide. So the pH will be lesser than 7. It will be an acidic solution. Third salt hydrolysis is a salt made up of weak acid and weak base. So it will be ammonium acetate. Now ammonium acetate, it will ionize to give us the acetate ion and ammonium ion. Further, the acetate ion and ammonium ion will interact with water, or it will, we can say, hydrolyze to give us the acetic acid and ammonium hydroxide. Now for this, when both are the weaker components, when acid is also acid which is formed is also weak and base which is formed is also weak, so this acetic acid, it will ionize to give us it will be present in ionized form. The ionization will not be 100%, since these are weak acids and bases. Similarly, ammonium hydroxide will also ionize to give ammonium ion and hydroxide ion. For the third case, to calculate the pH, we have a formula here. For these, we can tell it easily what will be the pH. But for the third case, the formula is pH is equals to 7 plus half pKa minus pKb. So it is if the numerical comes, what will be the pH of the resulting solution of a salt of weak acid and weak base, whose pKa values are given, pKa and pKb, then you can easily calculate the pH value using this formula. With this, this was all in the chapter Ionic Equilibrium. I hope you liked my video, and if you learned something new today, don't forget to subscribe my channel and do give your feedback in the comment section below. Thank you.